Right. Yeah. So basically, as I said, I had to stop it for a second because I'm just thinking out loud here. But anyway, this is the relationship between the displacement and the velocity, right? So if we had done a test and we actually measured velocities, we would say, well, but I'm not interested in the relationship between forces and velocities, V. I'm interested in the relationship between forces and displacements. Can I get it without having measurements of displacement? And the answer is yes. All you have to do is recognize that instead of CV, you need CD. And what is CD? CV times AC to the minus 1. So you just simply, instead of putting CV here, you put CV times AC to the minus 1, and you have immediately obtained the transfer matrix for displacements. Okay? So just take this. If you don't have CD from the test, but you have CV from the test, you just put CV times AC to the minus 1 there, and you just have what you want. Now, let's do one more. We have ACX plus BCU, y is equal to CDX, right? Then we have y dot is equal to CDX dot, and therefore y dot is equal to CD x dot being AC times x, right? And we just said that this is CV, so we can also write this as CVX because we know that the term BC, CDBC was 0. Now that we are here, we can look at another derivative, right? So for example, if I differentiate this again, I get CDAC times x dot, right? Or if I do it in this one, depending on whether I had displacements or velocities or whatever, they're all the same, I get CV times x dot, right? So if we follow this path, we can see that we have CD times AC multiplied times ACX plus BCU, right? Now let me erase this one out of the way. Let me keep on with the displacement part. So that means that what? That we have, should have said y double dot, right? So y double dot is CDACX dot. Y double dot is CDACX dot, or CDAC times this. Or y double dot is equal to what? To C, put the D on the wrong place. Right? Not to be confused with discrete time. So this is CD times AC squared plus CD times AC times BC times U, right? Now this is kind of cool, right? Because now let's look at this. What this says is if I had measured accelerations, the C that I would have, X. What this says is if I had measured accelerations, the C that I would have obtained in front of the state is actually CD times AC squared, right? So that means that you can say that the C for acceleration is just the C for displacement times AC squared, right? But even more, we got something even nicer here, or just as nice. We know that for acceleration, there may be a D. And if there is one, it has to be this, right? So we can also say that the direct transmission, had we done it, with acceleration would have been, well, depends what we think we have and what we are getting, but it would have been this, right? So let me clean it up and look at postulated scenarios. Let's say that what we did, what we had assumed, okay, let me try to be a little clear. Assume we measured accelerations. Assume we measured accelerations. So what we have is what? When we finish the analysis, we have A, B, C, and D, right? We have A, B, C, D. But, because there might be a D, because we measured accelerations. But I'm not interested right now on this thing. I'm interested on the relationship between forces and displacements, because I'm eventually trying to get flexibility or something like that. So I get my G, but if I get my G using the C that I got, which is C acceleration, times identity times S minus A to the minus 1 times B, then I just have relationship between force and acceleration. I don't want that. I want the relationship, this is for acceleration, right? I want the relationship for displacement. What is the transfer matrix for displacement? Then I say, well, I don't want CA here, I want CD. But what is CD? Is CA times AC to the minus 2, so I just get CA times AC to the minus 2 times identity times S minus A to the minus 1 times B, and eureka, I got the matrix I want, which is the force, which is the matrix connecting forces to displacements, even though I never measured displacements. I only measured accelerations, and it just pops out like that. Okay? So, this is also quite useful, right? This is quite useful because in practice, what is the cheapest and easiest sensor for structures, at least? The cheapest and easiest sensor is an accelerometer. So we normally, under most circumstances, find ourselves with acceleration measurements. So when we do the system identification, what we obtain really is CA, CA, B, and D. Now, D may still be 0 because it may be that the accelerometers are not positioned at the location where there are forces acting. And so even though we are measuring acceleration, the D might still prove out to be a 0 matrix. But independently of that, we obtained it, with or without a D. Now, we want to do some damage localization or something. And for that, we want to see how the transfer matrix has changed between the undamaged and the damaged condition, for example, at some S value. But we are not interested on how the relationship between forces and accelerations have changed. We are really interested on how the relationship between forces and displacements have changed, because that's what we got a feel for and so on. So even though we could not measure displacements, we know that the matrix that relates forces to displacements is simply this one, with CA AC to the minus 2. All right? If we had measured velocities, then this would be CV times A to the minus 1, and so on. So you've seen the relationships that I developed. These relationships are developed in a paper that I wrote quite a few years ago, and it's only a small part of the paper. The paper is really not, excuse me, it's not about those relationships, but they are used in the paper. I will, let's see. Yeah, I can probably post the paper, so if I find it, I'll put it in the website on Blackboard in case you want to read the original thing. The purpose on that paper was for something else, but there you can see a summary of this derivation. Okay?